still trying to think what happened to that calculation. Brain is in the back of your mind, it's not leaving it alone, right? I got here, I googled it, it's called sun synchronous orbit. Sun synchronous orbit. So if this is given to you on the test, you don't have to rederive this one. You can just use it as is, because it's such a common law. Got it?
I got 2.5 times 10 to the 10th.
Meters?
Yeah.
Well, that's pretty big.
I don't know, I might have messed up.
Because remember, 1 AU is 1.5 times 10 to the 11th. So that's the distance of the Earth from the Sun. So this one is only 10 times smaller than that. Then you would be, you would basically go around the, because the Earth goes around the Sun every 365 days. So that planet, that satellite would go around the Sun every 25 days, right? Others got that too? Yeah? Okay. So basically, it looks something like this. The satellite is here, and then the Earth is about 10 times farther away. So something like this. Now, I always like to visualize things when I get an answer. Right, so this is 1 AU. So the Earth is going around the Sun 365 days. This satellite is going around the Sun every 25 days. And the Sun is rotating every 25 days. You see? So this satellite will go around and over one point. And then you can study. So in the future, we'll probably have a bunch of satellites like that around the Sun, and they study one particular group of solar flares or maybe sunspots. So does that make sense visually? Yeah, sort of, right? So now if a satellite of 1,000 kilograms is launched from Earth's equator, so imagine this is the Earth's equator. Well, the equator is already rotating with a certain kinetic energy, right? And on top of that kinetic energy that it has due to rotation, now we have to launch that satellite with a certain extra kinetic energy, right? So this is a matter of energy conservation. We're going to argue the initial kinetic energy of rotation that it has due to the fact that it's on the Earth's equator, plus the kinetic energy launch, plus the initial potential that energy that it has due to the fact that it's bound to the Earth, must equal to what? When it finally gets there, we want it to have a certain total energy of orbit, right? So energy of orbit. That's the argument you use. the initial kinetic energy of rotation plus the initial kinetic energy of the launch plus the potential energy initial, right? So what's the initial kinetic energy of rotation? One half the mass of the satellite plus the velocity of rotation squared plus the initial kinetic energy of the launch plus the potential energy initial over the radius of the Earth, right? Because its initial potential energy it has because it's on the sitting on the surface of the Earth, right? Is equal to the kinetic energy of orbit, which is what? Negative g m m. What was the general equation? Negative g m m over 2d, right? The total energy of orbit once it gets there. And so now we're solving for this. Okay? So 1/2 the mass of the satellite. Velocity of rotation. What's the velocity of rotation at Earth's equator? If you don't know it exactly, then you can just do 2 pi times the radius of the Earth divided by the period of rotation of the Earth. 2 pi radius of Earth over the period of rotation, which is 24 hours, times 3,600 seconds squared. Right, so that's the velocity of rotation. 2 pi times the radius of the Earth over 24 hours that the Earth rotates. 3,600, then that's converted to seconds, then you square that. Plus the kinetic energy of the launch, minus 6.674 times 10 to the minus 11. The mass of the, this is the mass of the potential energy that it has with respect to the Earth, right? So minus mass of the Earth, mass of the satellite over the radius of the Earth. Is equal to what? Minus g times 10 to the minus 11 mass of the sun, not the Earth, right? Because once it gets there, now it has potential energy to the sun. Now, does it also have potential energy to the Earth? Yeah, but probably be negligible, right? The sun's potential energy dominates once it gets there. So now this is the mass of the sun. What was the distance? I just erased it. 2.5 times 10 to the 10, right? So now the mass of the sun over the mass of the satellite over twice that distance that we just found. Now, did I forget to include something? Yeah, I kind of did. How about the initial potential energy that the satellite has with the sun? You think it's negligible or it has to be included? Well, the sun's mass is pretty heavy, but you are very far from the sun. I'm not sure, is it negligible? Well, what would it be if I included it? Then there would be another potential energy here, negative 6.674 times 10 to the minus 11. Then there would be the mass of the sun, right? 2 times 10 to the 30th, 1,000, over your distance from the sun, which is 1.5 times 10 to the 11th. Now, is this negligible compared to this? If it is, then we could ignore it. You know? Well, this is 10 to the 30th over 10 to the 11th is what? 10 to the 19. 10 to the 24th over what's this? I want to do a ballpark estimation, right? So if I just compare this ratio, right? That's 10 to the 19. If I do, what is this? 6.38 times 10 to the what? 6, right? So if I do 10 to the 24 over 10 to the 6th, 10 to the what? 10 to the 18. Ooh, it would have been grossly error if I had ignored this. Then, you know, NASA would get on my case. Right? Oh, totally terrible. Now, what if the question said, I want the satellite to go and become a geosynchronous to the Earth, not geosynchronous to the Sun? Do I have to include the potential energy with the Sun? Or can I just ignore that if it's this? See, so do I always have to, in all my calculations, always worry about the potential energy with the Sun? Because in this scenario, I do have to worry about the initial potential energy with the Sun. Okay, so if the question said that I want the satellite to go and be geosynchronous to the Earth, so then what would happen? You would have this, you would have this, you would have this, then you would have, what would be the total energy? 6.67, this, no, then this one would be what? The mass of the Earth, this, over 2 times whatever distance that is, right? So it wouldn't be this anymore. It would be the distance from the Earth, and it would be the mass of the Earth. But then you would have another energy here. Once it's there, it also has energy with the Sun again. And then that would be GMM over D. But I believe that and this would cancel. You see? Why? Well, because if the satellite is here, the energy that it has with the Sun, and when it's here, the energy that it has with the Sun are roughly the same. Right? Because it's only going from here to slightly above the Earth's surface and becoming a satellite, right? So the energy with the Sun, even though it does have energy with the Sun, is not changing. So, 2 ends of the thing cancels. Right? I think I have that kind of question on my test review for the first test. I have a question, how much energy is required to be a geosynchronous, and then you don't even have to include the Sun. But on this one, you do have to include it. Okay, so now put all this mess in and calculate for kinetic energy of the launch. So this one, negative, negative goes all to the right. This one goes to the left. So then the energy becomes kinetic energy of launch this one goes to the right, becomes positive. This one goes to the right, becomes positive. And then this one goes to the right, it becomes negative. Okay, so I get negative kinetic energy. Negative 1.72 terajoules. What does that mean? So how does something like this come out negative? You've got two positives, right? And you got a huge negative probably. This is a huge negative. Or let's see here. See why 10 to the 30th? 10 to the 10th. That's 10 to the 20th, right? 10 to the 20th. Here you got 10 to the 30th, 10 to the 11th. So you got 10 to the 19th. So this is positive, but it's smaller positive than this guy. Right? And then here you got 10 to the 24th, so you got 10 to the 18th. So this is even less positive than that. That one doesn't change the answer too much, but it's an extra negative. So that means I don't have enough positives to counteract the negative. So what does that mean? Well, as soon as I launch, then the thing is going to spiral inward anyway. It wants to go towards less energy. So the energy that it has at the end, this energy that it has at the end is more negative. Well, objects already like to go towards more negative, right? So it almost feels like here, what do I have to do? I have to kind of shoot the satellite in the opposite direction. You see? Like this almost. Okay, so let's say it's going like this, and then here's the sun. So you have to kind of shoot it when it's, you know, maybe like, let's say something like this. So there's a little bit more mechanics and dynamics going on here. So let's say my head is the sun, and then the thing is spinning like this. So kind of like at this location when it's spinning away from the sun, then shoot it with a certain velocity, right? Then it goes, and then probably might spiral inward anyway, because it doesn't have enough velocity, you see? So the negative just means shoot it the opposite direction, so that by the time it comes to this location, it's not going too fast, and then it becomes a satellite of the sun. You see? Did you guys get that answer too? Yeah. If I were to change that to a velocity, what would that be? 1.5 times the mass of the satellite times velocity squared. So then that would be the velocity of the launch velocity. So then I would say, so 58.6 kilometers per second. That would be the launch velocity, but kind of shoot it in the opposite direction. See? Now, how would the answer change if you launch it from the north and south pole? then you can't use advantage of the kinetic energy of the rotation of the Earth. So this part is missing. Right? Then you're just going to have to launch it up or launch it this way. But the Earth doesn't spin at the top. So this part misses, then what happens? Then my answer becomes less negative, right? So then it becomes, let's say something like negative 1.55 times 10 to the 12 joules, right? So less negative. That means the velocity of the launch is going to be smaller, okay? So you're not using the kinetic energy of rotation of the Earth. Cool. So you could answer different kinds of questions like this. You can say, okay, what if I wanted to be a satellite of Jupiter, geosynchronous satellite of Jupiter? Calculate that distance, then use the same similar equation, and now it goes around Jupiter. You see? So you can do different things like that. Okay, cool. So a lot of good stuff with that chapter. We could keep doing more and more and more examples, but you have to practice. As you see, there's so many different situations, scenarios. Now we change the topic quite a bit. Go to fluids, fluid dynamics and statics. That'd be a good spot to stop it and restart it.